Talk about the exciting development made by Microsoft in the world of data center. Sirius, a flat data center network with nanosecond optical switching. As we all know, data is growing at an unprecedented rate due to the rapid development and adoption of digital technology. The amount of data being created and stored every day is increasing exponentially. How is this data stored, or how is this data processed? As we know, cloud systems maintains the data and are the biggest storage for the data. How does the cloud system works? Switching. Switching is a critical aspect enabling data to be efficiently and reliably transmitted between network nodes. This introduces us to Moore's law. Moore's law states that the number of transistors on a microchip doubles approximately every 2 years, which had driven significant advances in switching technology. As the number of transistors on the chip has increased, so has the complexity of the functionality of the switching devices. Using the different algorithms and techniques, it is possible to optimize network performances and reduce latency. But still, there is a growing concern in the industry that for how long this nice trend can continue. And it is also probably the worst time for this to happen because of the spike in traffic demand driven by the availability of different services. End of Moore's law for networking. Is it really? Let us check. A new chip that has twice the bandwidth of previous generation at roughly the same power and cost. But it comes with certain limitations. As a transistor becomes smaller and more densely packed, they generate more heat, making it increasingly difficult to dissipate heat efficiently. This limits the clock speed of processors and can also lead to other reliability issues. There are certain economic constraints and different alternative technologies like accelerator or GPUs, which can process the data in excess of tetrabyte per second. How did researchers come up with Sirius, or why is there a need of Sirius? So there is a question which they have answered is that can the traditional electronic switches be replaced? Traditional data centers networks based on electronic switching technologies such as packet switching, they have certain limitations in terms of scalability, throughput, and power consumption, which can lead to network congestion, high latency, and increased cost. Sirius systems addresses these limitations by using advanced optical switching technologies such as AWGR and tunable lasers to enable fast and efficient data transfer between servers and storage devices within the data center. It offers a flat topology which eliminates the need of multiple layers of switching and routing, reducing the network complexity and latency. This also, as the amount of traffic within the data center networks continues to grow, there will be an increase in need of higher bandwidth switching technologies. This will require development of faster and more efficient switching devices, such as optical switches. Um, Also, there is a growing popularity of real-time applications such as video streaming, online gaming, which needs low latency switching technology. This is also addressed by Sirius. There is an improved power efficiency due to the lower number of layers in the network, resulting in financial saving as well, and a smaller environmental imprint. There is increased flexibility and scalability, which allows to accommodate changing traffic patterns and to add new servers and components swiftly to the network. As we move to the post-Moore's law era, this paper presents a new concept of optical switching. So, what is optical switching, and why do we need optical switching? Let's take a look at it. Optical switching is a type of switching technology that uses light signals to transmit data with network. Unlike traditional electronic switching, which uses electrical signal to transmit the data, it uses optical fibers and photonic components to transmit and switch the data at extremely high speeds. Building blocks of Sirius system: AWGR, tunable lasers, and aggregated tunable lasers. What is AWGR? It's an arrayed wavelength grating router. So what is that? It is a type of optical device that is used in optical communication networks to multiplex and demultiplex multiple wavelengths of light. AWGR use an array of waveguides to split and recombine optical signals, allowing them to transmit multiple wavelengths of light simultaneously. In this system, AWGR is made up of a series of waveguides arranged in regular pattern, as well as a set of input and output waveguides. Each input waveguide is linked to a tunable laser that produces optical signals at a given wavelength. Based on the wavelengths, AWGR routes these signals to the output waveguides, enabling for efficient and rapid optical signal routing between the network devices. As we can see it in the image, the certain output port are diffracted or cyclically connected through the output ports that are extensively used, and these nodes are extensively used in wide area networks to multiplex and demultiplex multiple wavelengths onto the fiber. Aside from providing all connectivity between their ports at the physical layer, AWGR also has an advantage of being passive with no mechanical or electrical part and thus no power consumption. This makes them extremely durable. Furthermore, wavelength routing is independent of modulation format, which is used to encode data into the wavelength. Tunable lasers. If you've seen a typical semiconductor laser, it consists of a gain section that produces a range of wavelength and grating section that permits one of these wavelengths to leave the laser. A tuning current given to a grating part of electrically tuned laser modifies the resonant wavelength it emits. These tunable lasers can tune across 112 wavelengths with tuning latency of 10 microseconds. But the main difficulty with quick tuning is that injection of current into the grating section for adjusting the laser, which perturbs the gain section and generates the light. The combination of AWGRs and tunable lasers in Sirius network creates highly efficient and scalable network that can handle high bandwidth demands of modern data center. By using these advanced optical networking technologies, this network represents a significant step towards towards building a high performance data center network. But there are certain limitations, there are certain questions which have raised using tunable lasers, and how to solve those. Disaggregate tunable lasers. Using disaggregate tunable lasers, we improve the concurrency of the Sirius network with a millisecond optical switching. It also uses tunable lasers so it basically uses tunable lasers which can create different wavelengths on demands. It utilizes in particular concurrent creation of several wavelengths by allowing the laser to operate independently and generate distinct wavelengths at the same time. This is accomplished through the use of wavelength division multiplexing techniques, which allows many wavelengths to be transmitted over a single fiber optic line. Uh, there is a significant reduce this dampening technique could reduce the tuning latency, uh, and the reason for this is an ordinary tunable lasers has close connection between wavelength generation and wavelength selection, which imposes a fundamental constraint on how quickly they may be altered. The two components of disaggregated tunable lasers, a multi-wavelength source capable of producing many wavelengths at the same time, and wavelength selector capable of emitting only one of these wavelengths, addresses these perturbation problems, and it is used to create these two components are used to create an a proper network which gives fundamental benefits, because these techniques, even material they use, which is silicon or phosphide, to create these components, are optimized independently. There is a multi-wavelength light source design variant which employs a bank of single wavelength laser with an array of semiconductor optical amplifiers serving optical gates. As a result, the information that the output wavelength must be adjusted. SOA based wavelength selector changes from uh, laser to the second laser after it has finished tuning. The future sequence of the wavelength changes is known in advance, and this approach can be expanded to more tunable lasers. Let's take a look at Sirius architecture. The network topology of Sirius is a flat two-tier architecture. The network is designed to be highly scalable and flexible, allowing for easy expansion and modification as the needs of data center change. A flat topology of the network means that there is no multiple layers of switches or routers, which reduces the latency and improves the overall performance of the network. Sirius nodes are linked to entirely passive core network through a number of uplinks. Each uplink port is outfitted with a transceiver that contains tunable laser and linked to a grating via optical fiber. As we can see in the image shown here, the image depicts a small scale series topology with 4 nodes and 4 gratings. Each node's uplink port is connected to a distinct grating and can deliver communication to a different set of destination nodes. Commercially accessible gratings with 100 ports and lasers that can tune over 100 wavelengths allow each node uplink to reach an additional loads via appropriate grating. While Sirius topology is flat with no optical electron conversion for data transmitted between the two nodes, the topology also provides connectivity between any two nodes via only one of their uplink ports. As a result, with the basic direct routing, the nodes can only interact directly with percentage of their total uplink bandwidth. So this is addressed by the series routing method, which is discussed further below. Uh, let's take a look at routing and scheduling. There is a lack of queuing or backend processing inside the core network, which has a significant advantage in the series design, with all the queuing shifted to the nodes themselves, where it can be better handled. However, the lack of queuing necessitates traffic scheduling so that no uplink port on a net node receives traffic from multiple source nodes at the same time. The on-demand scheduling is one way, which involves passing the data center demand matrix as measured at the node to a scheduler, which calculates and assigns communication time slots to the nodes. In addition to the scheduling is also an important aspect of Sirius network. The network uses packet-based scheduling algorithm to allocate bandwidth, which fairly flows among the competing traffic. The algorithm ensures that each traffic uh, each traffic flow receives its fair share of available bandwidth. It also helps in preventing individual flows from monopolizing network resources and causing congestion. The network load balancing. The network is designed to handle high traffic volumes and high bandwidth demands, and load balancing helps to ensure that traffic is distributed evenly across the network. Link aggregation is a significant load balancing technology which is employed in this network. It combines many network links into single logical link, hence enhancing the available bandwidth between switches and servers. The network can spread traffic evenly across numerous physical links by employing link aggregation, which helps to further reduce the congestion and enhance overall network performance. Each node pair simply has to be connected uh, with their perfect match for the topology, and in the data center with n nodes and aggregate uplink bandwidth of b per node. Each node's transceiver is cyclically adjusted across all the frequencies. Uh, it also takes into consideration a round robin approach, wherein each node can communicate with all the nodes uh, at the top of read-time. Sirius also operates on fixed sites packets or cells provided by originating server. Traffic created locally on these servers is transmitted directly to the intermediary server in server-based configuration. Um, it has intra-rack traffic which is routed directly through the rack switch in the rack-based setup. Outside of this rack traffic, it is kept separate. It has a FIFO virtual queue and which is transmitted to the intermediate rack. Cells arriving to the rack switching via its uplinks are routed accordingly, either to a server within the rack or directly to the destination rack. Sirius allows a node to reach any destination node via any other node. That's the main advantage of Sirius. Throughput and latency. While Sirius cyclic schedule eliminates the need of data center wide scheduler, it does not necessitate an extra hop through intermediate node for traffic being between any two nodes. This can have a negative influence on both the network throughput and latency. However, the one significant benefit of load balancing technique is that it guarantees a worst case throughput across any traffic pattern, and it it can be no more than 2 times worse than that of the ideal non-blocking network. In a large data center with a spread of 500 meters, detouring traffic through an intermediate node can add an extra physical distance up to 500 meters, resulting in additional propagation latency of up to only 2.5 seconds though. The network epoch is 1.6 with 100 nanosecond time slots and 16 nodes connected to each grating, as a result of which every other cell queued ahead of it can or a cell can incur 1.6 seconds queuing delay. To maintain this end-to-end network latency, it is critical to minimize waiting and at intermediate nodes. But also due to but because of low queuing ensured by the congestion control, only small reordering buffer is required. Congestion control. Serious congestion control protocol attempts to reduce node waiting by demanding a round of request grants before cell can be transferred to an intermediate node. Each node has a local buffer that stores cell generated locally or received via one of the downlinks. Queuing occurs when many nodes send to them at the same destination via intermediary nodes during the same epoch. Um, uh, because of there are so many nodes in the network, there's so many data transfers, so many data transfers working simultaneously, uh, there is a need to achieve time synchronization. So how does this network achieve time synchronization? A time synchronization technique requires a it doesn't require, synchronization or proper regime. Receivers can extract the sender's clock from incoming bit stream and can change their lock to a local clock to match the frequency of the sender's clock. It to it also switches the leader every few epoch in the round robin method for increased robustness. To accomplish proper time synchronization, the propagation delay between any two nodes and their relative time offset must be accurately estimated. Um, and AWGR also uses a relative offset time, uh, which is a fundamental concept as it has a passive core which allows for accurate, efficient measurement of nodes' physical distance. This is used to calculate the time difference between the nodes when the fibers connecting nodes to the AWGR have different lengths. Knowing the physical distance of each node from the AWGR, it is also critical to ensure the correct system behavior. Challenges addressed by Sirius network. As data centers continue to grow in size and complexity, uh, it Sirius enables high scalability and reduces the complexity of the network. Uh, Congestion is a common problem in data center networks and can lead to reduced performance and increased latency. Sirius addresses this challenge by using optical switching, which can handle very high traffic volumes. Optical switching is also used for energy efficiency as it needs less energy than traditional electronic switching. Um, then for network reconfiguration, there is a dynamic data center environment, which often requires a response in changes in traffic patterns or in network failures. Uh, so, using the advanced technology like AWGR and tunable lasers, this enable it can enable a rapid and efficient network reconfiguration. Let's take a look at design. CMOS dependency. A server-based Sirius deployment offers an all-optical non-CMOS based network capable of interconnecting thousands of servers. Instead of rack-based, Sirius is still reliant on CMOS-based electrical switches for intra-rack connectivity. When no application data is broadcast, time slots are separated by a guard band to allow end-to-end path to be adjusted. Whenever two nodes are connected at a time slot, the fact that there are not perfectly synchronous means that the clock and data recovery circuitry must be trained in order for them to correctly sample the incoming bit stream. Standard transceivers have CDR latency of microseconds, which has been a major impediment to fast optical switching at a system level. Load balanced, let's take a look at fault tolerance. So the load balanced routing increases the blast radius of the failures, uh, failures such as transceiver failures because of any shared shared backups. The connecting rack pairs every few microseconds, on the other hand, allows for reduced overhead while detecting failures quickly. It also it reduces the loss of proportional loss of network bandwidth. Sirius system has been evaluated through simulation studies to analyze its performance under various traffic conditions and network configuration. These results have demonstrated that system is capable of achieving high throughput and low latency. Um, there has been tested it this system has been tested and developed and tested in real world scenarios to evaluate their effectiveness in the actual data center environments. It has also benchmarked against other data center networking technologies to assess its performance and efficiency. When compared to an electrically switched network with 4 layers of switches uh, and up to 6 transceivers, this network flat topology reduces the network power and cost by nearly 3 quarters. Uh, as we can see in the figure, electrically switched series variation is discovered to cost only 55% of this variant, as there is a relative power in comparison to a non-blocking ESN with changing overhead of tunable lasers. The simulated workload based on publicly available data center traces. A Sirius rack-based data center with 128 racks, each with 24 servers, and are used to compare the performance of the electrical network with Sirius. There is Sirius surpasses the electrical switch network in terms of both FCT and good put. Uh, there has been there has been tests which have found effective in terms of queue size on congestion control performance and memory occupancy by increasing the size of each individual queue uh, from few cells to more cells. The at a low load, no additional transceivers are required to match ECEN good output. But as network traffic increases, serious increased path length begins to impact the overall good put. Hence, there is a proper built-in uplink bandwidth and flow size of the data. To conclude, Sirius maintains power cost and efficiency in comparison to an oversubscribed electrical network by doubling the uplinks per node. It also approximates the behavior of an idealized congestion control while consuming little memory. The queue size is determined by FCT and throughput. Utilizing fixed size cells in series results in higher FCT and lower output as compared to utilizing variable size packets in ESEN for small flows of volume. Series fixed size cells outperform ESEN for larger flow size. Thank you so much. This was a short summary and presentation on series of flat data center with nanoseconds optical switching.